Okay, in this podcast, we're going to take a look at what's known as colligative properties. So let's start off by thinking about, we saw a lot of this summer, right? Trucks putting salts on the road. So why do they do that? Well, as you know, when the roads get icy or are threatening to be icy, they put the salt down. And what the salt does is allow the temperature to get colder before it freezes than it normally would. It's really similar to what you might see your parents do, maybe you do, when you're getting ready to boil pasta or something like that. See someone putting salt in the water. And while you may think it's being done for flavor, and maybe even your parents think it's being done for flavor, originally when people started doing this, it was to get the boiling temperature to be higher, so that once the pasta started cooking, the temperature started to boil, it would boil at a higher temperature and therefore cook faster. Okay. So, boiling point and freezing point are known as colligative properties. And a colligative property is a property that changes based on the amount of solute that is dissolved in the solution. And the interesting thing is, it doesn't matter which solute. It doesn't matter what its mass is. It doesn't matter what type it is. The only thing that matters is the number of particles. Doesn't matter what the composition of those particles is. It's the number of particles that are in that solution will determine how much things like boiling point, freezing point, and vapor pressure change. So these are three typical colligative properties. These are properties that change based on how much solute is dissolved in them. We're going to focus on boiling point and freezing point. Okay, so let's think about what happens when I put a solute or I dissolve something in water. Here is water. You can see the hydrogen bonding between these dashed lines, right? And here is water with a solute in it. The green things here you can consider to be a solute particle, something in there. So when you are freezing, when the water is freezing, these attractions form and pull the molecule together. And you can imagine when there is something, we can consider it an impurity, anything in the solution, they disturb that intermolecular attraction between the water, because if I have an ion here, or even a polar substance, it's also going to be attracted to the water, and it's going to disturb this crystal, and you end up having freezing point lower than what you would express. So we call it freezing point depression, because if I have a solute in my solvent, the freezing point, the freezing temperature will go down. Okay. I also can have boiling point elevation, which means the boiling point will go up if I have a solute dissolved. So here I have just water. Particles gain enough energy that they can escape and form this vapor above the liquid, right? That's boiling. But if there are solvents or solute particles in the way, it's going to disrupt how much of those particles go off into the gaseous state. Because of course these particles again are also attracted to the solute, either as ions or as polar molecules, preventing them from leaving. It's going to take more energy for them to leave. Okay, so boiling point elevation. Alright, so when we add salt to water, what happens? Any salt. So salt meaning ionic compound. But this will even happen with a molecular compound, so or a covalent compound, right? So the freezing point will go down, and we call it freeze. Because it goes down, we call it freezing point depression. We depress the freezing point. In boiling point goes up, so we call it boiling point elevation. The boiling point gets elevated. All right, so let's take a look at a problem, or let's take a look at how to solve these. So calculating FPD, freezing point depression, and boiling point elevation. So they basically have the same equation. There is this change in temperature of freezing point is equal to K sub F, which is a constant, and I can find that constant right here, and you will always be provided with it each solvent has a different K sub F, right? So it depends on the substance times the molality of the solution times this factor I. Now I is the dissociation constant. So if I have NaCl and I have 1 mole of that, it's a question of how many particles do I make. So I'd make an Na plus and a Cl minus. So for every one of these I get 2 particles. If I had, let's say, magnesium chloride, I would end up with a magnesium 2 plus 2 chlorine minus, so I would have 3 particles, so I would be 3. And of course, if I have a covalent compound, let's say like methane, it does not break apart, so I end up with the same thing. So my I is going to be 1, and that is always true when I have a covalent compound or what's considered to be a non-electrolyte. If the substance does not break apart into more than 1 particle, my I is known as 1. Okay, so let's take a look at how we use this. All right. Okay, so I'm asked this question: what is the freezing point and boiling point of a solution made from 25 grams of sodium chloride dissolved in a half a kilogram of water? So we know we're looking for the change in freezing and boiling point, so we're going to use the equation that you were provided with. Change in temperature at freezing is the K sub F for water, right, times molality times the I factor. So let's go ahead and indicate what we know, right? So we know K sub F. It was given to you in the previous slide. I don't know molarity, but I know molality is moles of solute over kilograms of solvent. And if I have 25 grams of sodium chloride, that is going to be 0.4277 moles. And remember, I'm going to carry extra sig figs until I get to the very end and then round for sig figs. So I'm going to put that in. And I have a half a kilogram. So when I calculate molality, I got 0.8554, carrying extra sig figs. So I'm going to add that to the equation up here, and I put the molality right there. And now I have to find what my I is. Now my I, like we said, sodium chloride breaks apart into 2 ions, so my I is 2. So I'm going to add I to the equation, and when I do that, I get 3.178. Now, if you look at it from sig figs, you might say, because I is 2, that's only 1 sig fig, but that's a counting number. It has an infinite number of sig figs. So we are limited to 2 sig figs by the 2 givens that we have, 0.5 kilograms and 25 grams. So we're going to go with 2 sig figs of 3.2 degrees C. So that is the change in temperature at freezing. But what it's asked me for is the freezing point and boiling point. So the freezing point is going to be whatever the normal freezing point is, and because freezing points get depressed, I'm going to subtract that change in temperature. So the normal freezing point for water is 0 degrees C. If I subtract this change in temperature, I'm going to end up with a temperature of minus 3.2 degrees C. Okay. Now that was the first half. The second half asks about boiling point. So boiling point is going to be the normal boiling point plus the change in temperature at boiling. So I've got to find the change in temperature at boiling. A little bit easier now because I've calculated a lot of these things already. My Kb is a given, right? My molality is the same. My I value is also 2, right? It's the same solute. So when I do this, I get an answer of 0.8896, which I'm going to make 0.89. And if I take that and I add it to the normal boiling point of 100, I get a new boiling point of 100.89 degrees C. Okay. Let's take a look at the next one. Alright, so here we are asked, when 5 grams of a non-electrolyte is added to 25 grams of water, the new freezing point is minus 2.5 degrees C, and we want to know the molar mass of the unknown compound. So I think the easiest thing to do is to write the equation for freezing point depression, because we know we're looking at a new freezing point, and see what information we have and what might lead us to get to molar mass. So here's the equation. Let's put in what we know. We know the change in temperature is 2.5 degrees C. We know the K sub F is 1.86 degrees C over molality. We do not know the molality of the solution, but because it's an electrolyte, we know that I is 1. I'm sorry, because it's a non-electrolyte. Non-electrolyte means it does not break apart into ions. So I'm going to end up with something that doesn't come apart, so I'm going to only have an I of 1. Okay, so molality is going to have to lead us to the molar mass. So let's figure out what molality is by dividing both sides by 1.86. And when I do that, I get a molality of 1.344. I'm going to carry some extra sig figs. Alright, so that's molality. So if we remember, molality is moles over kilograms. And what I know is molality is 1.344. I don't know moles, but I do know kilograms, because I know I have 25 grams of water. If I divide that, that's milliliters. If I divide that by, I'm sorry, that's grams of water. If I divide that by 1,000, because there's 1,000 grams in a kilogram, I get 0.025 kilogram. And if I put that in the equation and then cross multiply, I get moles equals 0.0336. Again, carrying extra sig figs. Okay, so I know how many moles I have, and I also know how many grams I have. It's given to me right here. And we know molar mass is grams over moles. My grams is 5.0, given to me in the original problem. My moles is 0.0336 moles. I divide that out, and I get 148.8. I only want 2 sig figs, because that's what all my givens have. So my molar mass is going to be 150 grams per mole. Okay, we're going to stop right there.